Hello everyone, in this lecture I am going to discuss about the numerical aperture, basics of optical fiber and some instruments related to the optical. So in the previous lecture I have discussed about the block diagram of optical communication system and general communication system, and I have discussed the difference between these two. So what is optical fiber? So optical fiber is a technology associated with the data transmission using light pulse traveling along with a long fiber, which is usually made up of plastic or glass. Metal wires are preferred for transmission in optical fiber communication as signal travels with fewer damages. So I have told you that why we are preferring this optical fiber in transmission or in communication. So in optical fiber, basically there are 4 layers, that is core, cladding, buffer and jacket. So inner layer is known as core and it is made up of glass or plastic with the higher index of the refraction than the cladding. Cladding is the upper layer of the core. If I talk about the dimension of this core and cladding, then you can see here it is almost 15 times the dimension of the cladding is almost greater than 15 times of the core. So and the refractive index of this core is, if I suppose refractive index of this core is N1 and the refractive index of this cladding is N2, then N1 should be greater than N2. So cladding is the glass or plastic with lower index of the refraction than the core. So we can define the core is a glass or plastic with higher index of the refraction, and cladding is the glass or plastic with lower index of the refraction. So if I compare the core and cladding with respect to the refractive index, then the core should have higher refractive index as compared to the cladding. Buffer is used to protect the fiber from damages and moisture, and jacket holds one or more fiber in a cable. So we can hold one or more fiber using this jacket, otherwise buffer is sufficient for protection and for protection of the optical fiber. So this is the structure of this optical fiber. Similarly, in optical fiber waveguide, the dielectric waveguide with core and cladding is used with suitable materials, and as I have already told you that the refractive index of the core is greater than the refractive index of the cladding. It is clear from this figure that the structure of the fiber will be like this: upper part will be the cladding and inner will be the core, and the refractive index, you can suppose this. This is the basic fiber structure. As I have told you in the previous slide that the core is surrounded by the cladding and cladding is surrounded by the buffer and buffer is surrounded by the jacket. So basically an optical fiber is a solid glass rod surrounded by the concentric glass shell as shown in this figure. This rod is called the core and is made of highly purified glass. Most of the light energy is confined to the core. The glass shell is called the cladding, which is surrounded by which the core is surrounded. The cladding shields optical fields so as not to get interfered by the outer layers of the fiber. So the cladding is an essential part of an optical fiber. The cladding is surrounded by the buffer layers these layers have no role in propagation of light. These layers are used for protection of this core and cladding. They are essentially to provide the mechanical support to the glass fiber and to protect from the external damage. So, this buffer is used only for the protection of this optical fiber. Now, what is the basic principle of transmission, or what is total internal reflection? This total internal reflection, because of this total internal reflection, the light propagates inside the optical fiber, or you can say that you can transmit the message to the optical fiber. What are the basic laws of this ray theory? The basic laws of ray theory are quite self-explanatory. In homogeneous medium, light rays are straight lines. If you are passing a light through a medium which is having same refractive index, then there will be no deviation in the incident light. So, that light may be absorbed or it may be reflected. If I am passing that light, if I am passing that incident light through the different medium that is having different refractive index, then what will happen? It will follow the Snell's law. What is Snell's law? Snell's law says that if you are incidenting a light on a normal, or you can say if a light is incident on a plane with some angle with the normal, suppose in that medium the light is having, the medium is having refractive index n1 and another medium is having refractive index n2, and suppose n1 is greater than n2. What does it mean? It means that the refractive index of medium 1 is greater than the refractive index of medium 2. It means we are moving from, if we are moving from medium 1 to medium 2, it means we are moving from denser to rarer medium. So, if I incident a light at this plane with some angle by the normal, then what will happen? If this light will propagate to the another medium, then it will move away from the normal, because the light is moving from denser medium to the rarer medium. So, it will move away to the normal, away from the normal. If suppose opposite to this, refractive index of medium 1 is less than the refractive index of medium 2, it means the light is moving from rarer medium to denser medium. So, and what will happen? It will move towards the normal. So, reflected rays, what are the basic laws? Reflected ray lies in the plane of the incidence and angle of incidence will be equal to the angle of reflection. In that case, if this follows the basic, if I am moving in the homogeneous medium at the boundary between two media of different refractive indices. Now, you can consider here the second case. At the boundary between two media of different refractive indices, the refracted ray will lie in the plane of incidence. Snell's has given the same law. Snell's law will give the relationship between the angle of incident and angle of refraction. You can consider if what Snell's has given is the statement, it has given the refractive index of medium 1, ratio of refractive index of medium 1 to medium 2 is, suppose this angle of incidence is this, angle of refraction is r, then what will be there? Sin r by sin I, or you can write sin I by sin r is equal to n2 by n1. So, this is the Snell's law, what I want to explain. So, now it is clear, if I am moving in homogeneous medium, then there will be no refraction. if I am moving from medium 1 to medium 2, it depends upon the from which medium to which medium you are moving. If you are moving from rarer to denser or denser to rarer, it will depend upon the medium and refractive index. If I am moving from a higher index to higher refractive index to lower refractive index, then what will happen? If I am moving from higher refractive index to lower refractive index, then the ray will go away from the normal. If I am moving from lower to higher refractive index, then the ray will move towards the normal. So, this is the basic principle. What is total internal reflection? So, you can see from this figure A, this is the high index N1 glass and this is the low index N2 air. So, I am interested, I am not interested here the values of the refractive index, I am interested here that the which medium is having greater refractive index, which medium is having lower refractive index. So, you can see here the incident ray is moving from higher refractive index to lower refractive index, or you can say the incident ray is moving from denser medium to the rarer medium. So, the angle of incidence is this. So, this light is moving from denser medium to rarer medium. So, it will go away to the normal. So, it is very obvious that this angle of incidence phi 1 will be less than the angle of refraction phi 2. This angle is made by the normal, made with respect to the normal. So, this angle of incidence is phi 1 and this angle of refraction is phi 2. So, what will be the if the light is moving from one medium to another medium, that it is not necessary, there will be the only chances of refraction. There will be the chances of reflection also, though there will be some partial reflection. So, the light that will be reflected from this plane or the boundary, it will reflect with the same angle of the incidence. So, the partial reflection will occur with the same angle of incidence, and the ray that is passing through the medium 2 will go away from this, will move away from this normal. So, this is the case 1. If I am moving from medium 1 to medium B, and if I am seeing this angle phi 1, incident angle is less than the incidence angle is less than the critical angle. If phi 1 is equal to phi c, so what is the phi c? Phi c is the critical angle. In that case, if the angle of refraction is 90 degree, if the angle of refraction is 90 degree, it means what is going to happen? This is the second case. This is the limiting case of the refraction, showing the critical ray at an angle phi c. So, what is happening here? This incident ray is going parallel to this boundary. So, this line will pass, the refracted rays will pass through go on this boundary, go away to the boundary. So, partially reflected rays will reflect and it will make the same angle, that is phi c. So, the critical angle is the angle at which the refracted rays goes on the boundary, or refracted rays make the angle of 90 degree with the normal. So, if it is making 90 degree with the normal, then it will move on the boundary of the two mediums, or you can say the connecting point of the two mediums, connecting plane of the two mediums. Now, if the angle of incidence is greater than this critical angle, if phi is greater than phi c, then what is going to happen? There will be no refraction. So, we have to see this. This case is known as total internal reflection. If I put the incident angle that is greater than critical angle, in that case we will observe the total internal reflection phenomena. In all the cases, however, you can see in figure A and B, there is a partial reflection in case A and B, but in case of case C, you can observe the total internal reflection, that is incident ray will reflected back to the surface medium 1. So, for meeting the phenomena of this total internal reflection, we have to follow the condition of this. Incident angle should be greater than the critical angle. What is critical angle? Critical angle is the angle in where the refracted ray is making the angle of 90 degree with the normal. So, this is the phenomena of total internal reflection. You can see here, this is the Snell's law. This is the optical fiber in which I have already told you that the refractive index of the core is greater than the refractive index of the cladding. So, here in this case, you can see here what will happen. So, I have already discussed this, that what is the condition of total internal reflection. We have to follow the phenomena of total internal reflection. So, what is the requirement and what is the condition for that? The condition is that the angle of incidence should be greater than the angle of critical. Critical angle से incidence angle greater होना चाहिए. Now, you can see here, suppose this is the point where the light is entering to the optical fiber. So, what will happen? It will follow the total internal reflection phenomena. Total internal reflection phenomena will, if it will follow the total internal reflection phenomena, then what will happen? It will make the same angle that the rays has made with the normal. So, this is the incidence angle, this is the reflected ray. So, it will make the same angle phi. Again, this will come to this. You can see here, this is the core and this is the cladding. So, light is moving inside the core. It is not passing the core, or it is not crossing the core. So, the light is moving inside the core. You can see here, this is the refractive index. So, then this optical fiber, the transmitted light in the optical fiber is following the total internal reflection phenomena. So, according to the Snell's law, if I change, suppose from here, if the light is entering from this point, so you can see here the light is coming from the air or medium 1 to the medium 2, that is core. So, in that case, if I follow this refractive index, this Snell's law, then this will be it will follow sin phi 1 by sin phi 2 is nothing but n2 by n1, where n1 is the refractive index of the first medium and phi 1 is the angle of incidence, where and n2 is the refractive index of the second medium and phi 2 is the angle of refraction. So, this is the Snell's law. According to Snell's law, we can find the angle inside the core and we can easily find the value of critical angle as well as the numerical aperture using this. Now, what is the critical angle? I have already defined this critical angle. When the angle of refraction is 90 degree to the normal, the refracted ray is parallel to the interface between the two media, or you can say the interface between the two media is nothing but the boundary of the medium 1 and medium 2, which is connecting all these two mediums. So, when the angle of refraction is 90 degree to the normal, the refracted ray is normal to the interference between the two media. In this case, the incident angle is called as the critical angle. So, critical angle is nothing but the incident angle when the angle of refraction is 90 degree to the normal. So, the same angle of incidence is called the critical angle. So, how can you define this? So, when you are making this, Snell's law says that sin phi 1 by sin phi 2 is equal to n2 by n1. Phi 1 is the angle of incidence, phi 2 is the angle of refraction. So if I am moving from medium 1 to medium 2, then I am saying this, if this angle phi 2 is 90 degree, then you will get this condition. Then phi 1 will become phi c. Phi 2 is 90 degree, then phi 1 will become phi c. Then what will you get? Sin phi c upon sin 90 is nothing but n2 by n1. This 990 is nothing but 1. So you will get this sin phi c is equal to n2 by n1. If the angle of incidence is greater than the critical angle for a given setting, the resulting type of reflection is called the total internal reflection, and it is the basis of this optical fiber communication. So as I have already told you that this we are following the phenomena of total internal reflection whenever we are transmitting a light ray in a perfect optical fiber cable. You can see here. Now what is the acceptance angle? The angle at which this refraction occurs is crucial, because this particular angle will dictate whether the subsequent internal reflection will follow the principle of total internal reflection or not. So this is the critical angle, you can see here. So this is the angle of incidence, light is entering in this at this point. So what is the acceptance angle? Acceptance angle is that angle in which the refraction occurs is because of this particular angle. So how will you find this acceptance angle? Acceptance angle will provide at which angle you are incidenting this incident ray to the core. So if I am moving from this angle to this angle, then the total internal reflection phenomena will occur. If this angle of incidence is increasing, if I increase this angle of incidence, then radiation, or you can say the refraction, will occur. So what will happen? So the loss of radiation will start occurring. In that case, the masses can be lost, or it can be there will be some security issue in that case. So the angle of acceptance can be calculated using this phenomena, and by using this, if this angle of incidence is equal to the critical angle, in that case, if this angle of incidence is greater than this critical angle, in that case it will not be in the range of the acceptance angle. So it will be quite difficult to calculate this angle, and the security issue will occur here because of the radiation loss. So the only rays with the sufficient shallow gazing angle at the core cladding interface are transmitted by the total internal reflection, and it is clear that not all rays entering the fiber core will continue to propagate down in its length. So from this figure you can say that what is the meridional rays. I will discuss this in later. From the figure, meridional rays and the array enters the fiber core at an angle theta a to the fiber axis and is refracted at the core interface between transmission to the core cladding interface at critical angle. So this ray to be transmitted by total internal reflection within the optical fiber core. So for the rays to be transmitted by total internal reflection within the fiber core, there must be incident on the fiber core within the acceptance angle, and the acceptance angle is defined as the maximum angle to the axis at which light may enter the fiber in order to be propagated, and is often referred as the acceptance angle for the fiber. So, if this maximum angle of the axis at which light may enter the fiber, maximum angle to the axis at which light may enter the fiber, this is the maximum angle. So, you can say the range in positive and negative will give a cone, and within that range of the cone you can incident the light, and it will follow the total internal reflection phenomena. If the incident ray is beyond the acceptance angle, or you can say that is the maximum angle, so I have already told you that there will be some loss of the information, where the incident ray be at an angle greater than theta is refracted into the cladding, and eventually it will lose the radiation. So, there will be some security issue. Now, what is the numerical aperture? So, in this figure you can see that the light ray is incident on the fiber core at an angle theta 1 to the fiber, which is in the range of the acceptance angle, or you can say this theta 1 is less than the theta a. So, this ray enters into the fiber, and numerical aperture. What is the numerical aperture? Numerical aperture is the ability of the optical system to collect all of the incident light on it. So, this is the ability of the optical system to collect the incident light on it in one area. So, from where we can collect all the light? We can collect all the light if I am having the proper acceptance angle. So, you can say, I will discuss this how it is related to the acceptance angle in the next lecture. So, this numerical aperture is directly related to this acceptance angle, because this is giving the information about the ability of the optical system to collect all the light incident on it in one area. So, a numerical aperture of the optical fiber is the light collecting efficiency of the fiber, and is measure of the amount of light rays can be accepted by the fiber. So, you can see here, this is the measure of the amount of light rays which can be accepted by the fiber. This parameter also, this numerical aperture also tells that we take an optical fiber and put it in the front of an optical source, then how much light is collected by the fiber from the source. Smaller the value of numerical aperture, the value of maximum launching angle, and smaller is the power accepted by the fiber. So, if the value of the numerical aperture is small, then the power accepted by the fiber will be the small. It means the acceptance angle is also less in that case. So, you can say here the numerical aperture is directly related to the acceptance angle. Now, let us take an example from where we have got this. This is the, you can find this numerical, find this formula using this. This is the air, and this is the, you are entering in this medium. So, you can write here sin theta 1 upon sin theta 2 is equal to n1 by n0. So, sin theta 1 by sin theta 2 is equal to n1 by n0. So, we have to find this, what will be the value of sin theta 1. So, we can find here, this is the angle of incidence. So, we can calculate here. After calculating, we can get here that theta numerical aperture is equal to n1 square minus n2 square whole square. So, because n1 is equal to n0 is equal to 1 in this case. So, we can find here We can write this formula. Numerical aperture is nothing but under root n1 square minus n2 square. So what is in this numerical, you can see here a silica optical fiber with a core diameter large enough to be considered by the ray theory analysis has a core refractive index of 1.50 and cladding refractive index of 1.47. So we have to find the core cladding and the critical angle at the core cladding interface. It means we have to find the value of phi c. What is numerical aperture for the fiber and what is the acceptance angle theta a. So what will be the value of phi c? Phi c is nothing but sine inverse n2 by n1. How will you calculate phi c? Critical angle is the incident angle in which refracted angle, or you can say refraction, angle of refraction becomes 90 degree, or you can say after refraction the rays goes to the parallel to the boundary. So here you can see here sine theta 1 by sine theta 2 is equal to n2 by n1. If this will become 90, then you will get then theta 1 will become phi c. So sine phi c will be equal to n2 by n1. So you can write here, after calculating you can find this value using the calculators. So numerical aperture is given by this formula, and numerical aperture is under root n1 square minus n2 square. N1 and n2 is given to you. Now third is acceptance angle in air for the fiber. So what will be the acceptance angles? Acceptance angle is, we have already found this numerical aperture. Numerical aperture is nothing but sine theta a. So we have to find the value of this theta a. Theta is nothing but sine inverse of this numerical aperture. Numerical aperture is 0.30. So you can find the value of theta a. Now this is all about the numerical aperture, total internal reflection phenomena, and Snell's law. What is critical angle, what is the critical angle, and how can you find the value of critical angle, how can you calculate the acceptance angle, how can you calculate the numerical aperture. So these are the basics that you can find. After viewing this lecture, you can discuss. If you have any problem, you can give comments in your comment box. Thank you for watching this video. Thank you.